Hey everybody, so these are some final exam review questions based on diagnostic questions that a lot of you had problems with. So I'm just going to go through these. They're basically a bunch of multiple choice questions, and hopefully these will be helpful for you in studying for the final exam. Excuse me. So here we have two strings of equal length attached to each other and set in the vibrating pattern as shown. And based on the standing wave pattern, we want to figure out which one has more mass or if either of them do. Now, we kind of already clued in that this green one is probably the heavier one, but let's try to make sense of this. So let's compare the wavelengths of these two things. So here, I've got a wavelength that is this whole distance, so basically half of the string length. Here, I've got a wavelength that is actually smaller than half the distance. It's a third of the distance. So the wavelength of the blue side is actually less than the wavelength of the green side. These guys both will have frequencies that are the same. So we've already talked about this. If the frequencies weren't the same, where these guys are joined together, would get torn apart. So this means that if V is equal to F times lambda, and lambda, F is the same for both of them, but lambda blue is less than lambda green, this also means that V blue is less than V green. Finally, if we look at how we get wave speed from the physical setup, so we have tension and linear mass density, so V is equal to the square root of tension over linear mass density. These guys both have to have the same tension because they're attached. So however much the blue string is pulling on the green has to be the same as however much the green is pulling on the blue. This means that for these guys to have different wave speeds, they would actually have to have different linear mass densities. Since V of blue is lower than V of green, that means that this quantity for blue needs to be lower than this quantity for green. If this quantity for blue is lower than this quantity for green, then that means that the denominator actually needs to be higher for blue. So this tells us that the linear mass density of the blue side is higher than the linear mass density of the green side. This is actually kind of counterintuitive based on the picture, but that's because the picture was actually one of the wrong options from the diagnostic for a very similar question to this. So that was that the blue string is heavier. All right. A next question, which is very similar, is we've got a standard wave pattern shown at the top. So this was a clicker question we did in class. And suppose the tension is quadrupled while the frequency and length of the string are held constant. Which standing wave pattern is produced? Well, here again, we're going to start with this idea that V is equal to F lambda, but V is also equal to the square root of T over mu. So one way we can take this is rearrange it and say, well, this means that lambda is equal to 1 over the frequency times the tension over mu. If the tension is quadrupled, but the frequency stays the same, and the length of the string is held constant, and it's still the same string, it means the only thing that's changing in this equation is the tension. Now we can do this, let's do this with a quick proportional reasoning. So what we'll do is we'll go lambda 2 over lambda 1 is equal to 1 over, since the frequency is constant, we don't need to put a little subscript on it, I'll show you that in a sec. And then we'll say tension 2 over mu. Again, the tension is constant, so, the linear mass density is constant, so we don't need to put a little subscript here. And then we've got 1 over F, and then again, square root of T over mu. The frequencies here, since they're the same, they're not changing, those cancel out. The linear mass densities cancel out. And this thing, the only thing that's left is the T2 and the T1. T2 is at the top here, the T1 is at the bottom there, so this looks like T2 over T1. Now T2 over T1 is 4, right? The tension has been quadrupled, so this is going to be the square root of 4, which is equal to 2. This means that after the tension is quadrupled, the wavelength has been doubled. If this is the original standing wave, and we want a wavelength that is twice as high as this one, that means if this is the wavelength for the original wave, and we want one that is twice as long, that means we need something that is going to be a wavelength that looks like that, right? And so if we look at our standing waves, that means it should be that one. Now we can do the same sort of idea, but instead we can go with one that is 4 times as heavy. And so instead of changing the tension, we're going to change, excuse me, we're going to change the linear mass density. We can take our equation that we had from our proportional reasoning one and go mu2 or lambda 2 over lambda 1 is equal to, now here we're going to have 1 over frequency again. We're going to have our tension, but our tension isn't going to change, so I'm not going to put the subscript there. I'm going to put the subscript with the mu. So that's going to be 1 over f, and it's going to be t over mu1. Again, our things that are the same for both cases, the frequency and the tension are going to cancel, and now we've got 1 over mu2, square root of that, over 1 over mu1. This looks like mu1, square root of mu1 over mu2. Now the square root of mu1 over 2, if we've made this thing 4 times as heavy, that means mu1 over mu2 is now a quarter, because mu2 is 4 times higher than mu1. Or I could do it like this, say mu1, and then mu2 is 4 mu1. Those cancel out. We get the square root of 1 over 4, which is 1/2. Now if we go to a situation where we have a wavelength that is now 1/2 of the original standing wave, if this is our original wavelength, then half of this should be our new wavelength. So that would be a wave that would look like this, and of course continue on like this. So that one looks like C. Here's another one that we did in class. We've got a string of length 1.2. It's fixed at both ends. Which one is not a wavelength of a standing wave on the string? So if we've got this and this thing is 1.2 meters here, so I'm just going to draw a few of these, but this first one would correspond to a wavelength of, what's actually, if this is 1.2 meters, the wavelength of this thing is 2.4 meters, or 240 centimeters. So this would be a 240 centimeter one. The next one, the next possible harmonic, is our second one. And again, the distance is 1.2. And now here you can see the wavelength here is 1.2, so that's 120 centimeters. Then the next one is going to be the third harmonic, and what's going to happen is the wavelength here is going to be this distance, which is, so this is the wavelength. That wavelength is 2/3 of 1.8. Or sorry, 2/3 of 1.2. So 2/3 of 1.2 is 90 centimeters. And then we can go and do one more and do this one. This one is the wavelength is going to be half of the string length. So this last one is going to be a wavelength of 60 centimeters. So you can see that the one we don't get is the 180 centimeters is the one that's not possible. All right, next. So here we have three objects with identical volumes. They're submerged as shown. And the question is asking which object or objects experience the largest buoyant force. Now, if these guys all have the same volume, well, let's step back a second, actually. The buoyant or buoyancy force is equal to the amount of water that the object displaces. So for two objects, like these two, that have the exact same amount of volume underwater, are going to have the exact same buoyancy force. It doesn't matter how they're underwater. It doesn't matter that this one is actually heavier than this one and needs to be held up by a string. They are going to have the same buoyancy force because they have the same volume underwater. Number 3, on the other hand, is only partially underwater. So the amount of volume of water that it's displaced is less than 1 and 2. Therefore, the buoyancy force acting on this thing is also less than 1 and 2. So 1 is equal to 2, but those guys are going to be bigger than 3, which means who experiences the largest buoyancy force is 2 of the blocks are equal here, and it's 1 and 2 that are the ones that experience the largest buoyancy force. The next question, we looked at this one in class, and so we have a fast-going ambulance goes by, it's got a siren frequency of 1,000 hertz, and the question is which of these graphs best represents, for part 1 here, the sound you hear as the ambulance passes by and just about hits you. It goes just directly toward you, right by you, and directly away from you. And so in this case, one of the things we have to really recognize is that our Doppler shift, if the object is going directly toward you or directly away from you, there's no change in the Doppler observed frequency based on how far away the object is from you. So if we have our our Doppler equations, which look like f prime is equal to f naught times 1 plus or minus the v observer over the v of the wave, divided by 1 minus plus v of the source over v of the wave, you can see in here that there's nothing to do with distance, and there's nothing like these are just the speeds of the object, of the observer and the source and the wave. Nothing to do with the distance from between the observer and the source comes in here. So as long as the thing is going directly toward you or directly away from you, you're going to have a Doppler shift that is just a constant frequency. So that is going to be like a piece that looks like this when it's coming towards you, because it's going to be a higher frequency when it's coming towards you, and here when it's coming away from you. So for part 1, this is going to be the correct answer. Now part 2, if you're standing further away from the highway, what happens is that the source is actually moving. It's moving toward you. When it's far away, basically all of its speed is moving toward you. But as it gets closer and closer and closer, there ends up being only kind of a small fraction of its total speed that is actually moving directly toward you. And there's even a time when it's basically not moving toward you at all, because it's driving completely perpendicular to where you are. As a result, you actually do get, in the case where you're actually quite far away from the path where the ambulance is going to travel, you actually do get an effect where the distance between you and the source matters. And that is because of kind of the component of the ambulance's velocity that is in your direction. These are the components of the velocity that are in the direction of the thing. So the VO is actually the component of the observer's velocity that is in the direction of the source. Vs is the component of source's velocity that is in the direction of the observer. So you can have in that person's direction, and you can have perpendicular to that direction. As a result, for part 2, this means you're actually going to have more of a gentle change from the maximum 1080 down to the minimum 920. It's still going to hit those extreme values, and as it gets further away from you, it's going to effectively become constant. But when it's somewhat nearby you, it's actually more of a gradual change, because not all of the ambulance's velocity is going in your direction. So for part 2, it would be part D, or option D. Here we have a beats question. Basically, we have two tuning forks. They emit frequencies of 523 and 527 hertz, and the question is, what do you hear? Well, you hear two things. First of all, the average, the sound you actually hear is the average of these two. So kind of the frequency that you hear is equal to the average of these two divided by 2, which is going to equal 525 hertz. That's the tone that you hear. Now you're also going to hear the beat that is due to the difference between these two. So F beat is going to be the 527 minus 523, which is going to be 4 hertz. Now, this means that the sound is increasing and decreasing in volume at a rate of 4 times per second. That's what this 4 hertz is. So we've got an average sound that we hear, the tone is 525 hertz, and the volume is appearing and disappearing, or getting, excuse me, is getting louder and quieter 4 times a second. All right, so the next question we want to look at is a destructive interference question or a constructive interference question. And so we've got two speakers. They're separated by some certain distance. So 2 speakers each have a wavelength of 2 meters. Speaker 1 is 8 meters away from you. And speaker 2 is 4 meters away from you. And at this point, you hear constructive interference. If we look at what the path length difference, which we've been calling delta x, is to go from speaker 1 to the person and speaker 2 to the person, there's a distance of 4 meters here, right? So that is the path length difference. So this is 4 meters. In terms of wavelengths, this path length difference is 2 full wavelengths, which we kind of would call 2, m is equal to 2. Now, if we want to go to destructive interference, we want to have the path length difference be a multiple of 2 meters plus an extra meter so that you go from the constructive interference situation to the destructive interference situation. This means what you want to do is you want to move speaker 1 to the left by 1 meter, and if you move speaker 1 to the left by 1 meter, that means the new position for this thing is going to be at 9 meters. So that's the condition that's going to give you destructive interference. If every 2 meters you're going to get constructive interference, so at path length difference of 0 meters, 2 meters, 4 meters, 6 meters, you're going to get constructive interference. At path length differences of 1 meter, 3 meters, 5 meters, and so on, you're going to get destructive interference. In this case, you would go from 4 meters at constructive. 4 meters is going to be constructive. And then if you move it over 1 meter, which is half a wavelength, you're going to get destructive. Right, this is, we've seen a question like this on worksheets and on the diagnostic. There's a whole bunch of different things here that are from the worksheets, so let's just go over these real quick. So we've got this thing spinning around, t is equal to 0, the dot is right here. Which of the graphs corresponds to x position versus time? Well, along the x-axis, I'm starting at some positive x value. It's going to start decreasing all the way till it's negative, and then start increasing until it gets back to some positive value. We know that these are going to be sinusoidal, and so part A is going to be graph F because it starts at a positive, decreases down to negative, and so on and so forth. Now, how about which of the graphs corresponds to angular position versus time? Well, angular position is usually measured relative to the x-axis, so kind of as the dot moves around, this theta would represent our angular position. If this thing is rotating at a constant speed, our angular position is going to rotate at a constant speed. It's going to start at 0, since that's right, along the x-axis is 0, and it's going to increase at a constant speed. That would be graph A, where you start at 0 and you got something that increases at a constant speed. Which of the graphs corresponds to x velocity versus time? Well, x velocity, if there's two ways to do this. If we already did x position, we know that to go from a position to a velocity graph, you just need to differentiate the graph. So if f is my position graph, I differentiate this. That means I'm going to start at 0. It's going to become negative, and then I'm going to get back to 0 and then become positive again. So I'm starting at 0. That's going to be g, gets negative, goes back to 0, becomes positive. So that's the one that we want, but let's just take a look at this in terms of just trying to reason through it, just looking at the rotating bike wheel. When at time is equal to 0, this yellow dot is moving perpendicular to the x-axis. That means there's no component of velocity in the x direction. As this thing starts to move around here, right, so that's my velocity initial. Right? As you get over to here, the instantaneous velocity of the yellow dot at any point is going to be a line that is tangent to the bike wheel. So we're moving completely to the left. Now this is completely in the negative x direction. Then it's going to go back to 0 because it's going to be over here. Then it's going to go over to here, and it's going to be in the positive x direction. So 0, negative x, or 0, negative, 0, positive. Right? 0, negative, 0, positive is g. How about angular velocity versus time? Well, if we do the differential piece, in part A, we figured out angular position looks like this. If we differentiate this, we're just going to get a constant. Right? The slope of this graph is a constant. Or we can just think, okay, if this thing is rotating at a constant rate, and you ask me, what is the angular velocity? Constant rate means that it has a constant angular velocity, and it's going in the counterclockwise direction, which, since our angles are defined as positive in the counterclockwise direction, this is going to be the one that is positive. So two different ways to look at this. Either we can differentiate graph A, which was our angular position, and we would get C, or we can just look at this and think through it and say, okay, well, this thing is rotating counterclockwise, and that's going to be a positive constant angular velocity. The last one is that if we assume that graph H shows our x position as a function of time, so that this is graph H, this is going to be x position as a function of time, what is the initial angular position at t is equal to 0? Well, this is saying that the yellow dot is starting at negative x, right? So this is our position as a function of time. It's starting at negative x, going to 0, going to positive x, back to 0. Where is negative x? Negative x is over here. So this is going to be the far left side. All right, so we have some true or false questions. As you might remember from class, basically anytime we have two strings that are attached together and we ask about what happens when you go with a wave from one string to the other, all those things translate to what happens when you go from a medium with a certain index of refraction to a medium with a different index of refraction. All these things are the same. So, true or false? So the first one is the wave speed is the same in glass and in air. Well, we actually have a definition for the index of refraction, which is, oh, that's wrong, hold on. we have a definition for the index of refraction, which looks like the velocity of the light in a medium that has an index of refraction n is equal to c divided by n. That means the bigger the index of refraction, the slower that light travels in it. This is a bit counterintuitive because you're always taught that the speed of light is a constant, but it's really that the speed of light is a constant in a given medium. So in the glass, the speed of light is actually lower than in air. So this is false because they are not the same. The frequency is the same as glass as in air. Well, this is the same as if we're talking about the two strings that are joined together, and you have a frequency in one string. It has to be matched by the frequency in the other string, or else those things are going to tear themselves apart. This is the same as the light that is going from the boundary of, or going across the boundary, so going from air into the window. You're going to need to have the same frequency for that light for the same reason that you basically need the same frequency for going from one string to another. So these two frequencies are going to be the same. The wavelength is the same as the glass as in air. Well, there's two different ways to think of this. The first is just to say, okay, I know that the speed of light in a material is going to be given by its frequency times its wavelength in that material. So if my frequencies are the same and my speeds are not the same, this means that the wavelengths are not the same. Okay. The other one is we can look at, this is something that you've been given on your formula sheet and you can just have a quick look at, the wavelength of light in a certain medium is equal to the wavelength of light in the vacuum divided by n, the index of refraction in that material. So if you go into a material with a different index of refraction, your wavelength is going to change. Your frequency will stay the same, and your wave speed will also change. This is one from a Bernoulli's equation. So Bernoulli's equation tells us that we have a pressure term, we have a kind of a potential energy term, 1g y times rho, and then we have a kinetic energy term, which is 1/2 rho v squared. Forgive me if I didn't get any of those exactly right, but it's still the same right idea. Oh, this isn't half. Ha ha ha. Right. So the idea here is that when you blow across the top of this straw, because this term is now going to increase, the pressure at the top of the straw is going to have to decrease. If the pressure at the top of the straw decreases, this is actually going to pull some of the fluid up through the straw. So when you blow over the top of this, it's actually going to pull the fluid in the straw up just a little bit, and so the fluid level becomes higher than the level in the cup. Here we have a position versus time graph for a mass attached to a spring that's oscillating back and forth. And so the question is, what does the velocity look like? What does the acceleration look like? Well, there's a few different ways you can think of this. First of all, you could just kind of brute force. This is just a graph. If I want velocity from a graph of position, I would just differentiate this. That means the slope of this point right here is going to be positive, so we're going to expect v to equal positive. If we think of it in terms of the simple harmonic motion, what you have is your mass being at the far positive end, going toward zero, being at the far negative end, going toward zero, going to the far positive end. So here, at this point, it's in the middle of going to the far positive end, which means its velocity would need to be positive, because that's the direction it's going. Acceleration, on the other hand, we could differentiate twice, or again, we could kind of reason through it. I mean, the rule of thumb is just that the acceleration is in the opposite direction of the displacement. Where does this come from? If you have a mass on a spring and you displace it away from the equilibrium position, the spring wants to apply a restoring force that takes it back to the equilibrium position. So if you displace it in the positive direction, there's going to be a restoring force in the negative direction. And the restoring force is going to result in an acceleration from F is equal to ma. This means for a positive displacement from the equilibrium position, you're going to get a negative acceleration. So positive velocity, negative acceleration. And I believe that is all of the review questions we had. So I hope you found these helpful, and see you for the final.